Hello, I'm Yousra Aafer, and I'll be presenting our work on auditing APIs via upside security specification. So this work was led by my student, Parjanya Vyas, who couldn't come because of visa issues. And this is a joint work with Asim and Asokan. So to provide some quick background, here we have a high-level overview of Android software stack. As we see, it's composed of 3 layers. And the framework layer contains system services, and these services expose APIs to applications. So some of these APIs are public, they belong to the SDK, and others are private. And some private APIs are vendor-specific. So APIs provide access to sensitive functionality, so they enforce access control, as you can see here. So this is an example of an access control. Now, a question that has long been asked by the security community is how effective is this access control model? Well, it turns out that answering this question is very difficult because we have no security specifications or very incomplete security specification, particularly for Android private APIs. So an approximate solution that has been proposed by the literature is inconsistency analysis. So let's compare access to the same resource if across different APIs. If they enforce different access control, then that's a potential vulnerability. So inconsistency analysis is not an old idea. The first 3 work, Kratos, Asteroid, and AC Minor, identify inconsistencies within the framework. So basically, 2 APIs lead into the same resource. Now, last year, 2 work have been proposed that propose to perform inconsistency across layers. IA's Finder performs cross Java and native inconsistency analysis, and Fred performs inconsistency analysis across APIs that lead to files and files access control. WoW, which was also proposed last year, performs inconsistency analysis via probabilistic inference. It assumes that access control to resources is not certain, so it uses probabilistic inference to resolve the inconsistency. Now, what can we see missing here? What about the application layer? Well, the principle of complete mediation states that when a preloaded application enforces access control before invoking an API, then the API itself should enforce access control. A lapse in the framework or the API implementation means that there is a potential vulnerability. So let's look at the following motivating example. So this is a private API introduced by a vendor. It allows manipulating secure folder policies, including what are the apps that should not be disallowed from being installed. As we see here, there is no access control. So we can speculate that this API might be problematic. Now let's look at the invocation sites in apps. So we identify 2. The first invocation site is a broadcast receiver. It enforces an access control right here. This is a permission. Now, the second invocation site enforces another type of access control. It asks the user to enter her password, and then she has to click continue, and then she would actually land into the secure folder activity, which leads to the secure folder policy. Now, beside these 2 access control checks, we see 2 programmatic checks, the one in red. So the user ID should be more than 150. Now, our initial speculation that the API was not properly protected is correct based on this app-side security invocations. Now, in this project, we aim to leverage similar insights. We want to audit framework API via app-side security specifications. But this stack faces 3 challenges. The first one, app-side security indicators are diverse. And second, we need to estimate the contribution of an API to an app component. And third, we need to understand the invocation context of an API in an app component. Due to time constraint, I'm not going to cover the last challenge. Please refer to our paper for more details. For the first challenge, app-side security indicators feature substantial diversity. They can use traditional access control, like permissions or UID checks, so these are easy to detect. Now, they can also use UI-based sensitivity indicators. For example, a text indicating a sensitivity, like, for example, password. They could use some type of alert dialogues. They could use also non-disposable UI elements. You can't really dismiss that UI. and then multi-confirmation. Here is an example of an alert dialog. So we know that if you click on this yes, the operation behind that is probably privileged. And this is an example of a multi-confirmation. So in order to encrypt a device, the user would first be facing this dialog telling him more detail about the encryption process. After he clicks here, again, we have an additional dialog saying that this operation is irreversible. So this multi-confirmation highly indicate that this operation behind this button right here is probably privileged. So besides this, we need to estimate the contribution of an API to an app components. We know that Android apps or components tend to be quite complex. So along the call side of an API, the components may invoke other code, for example, internal methods, calls to libraries, and so forth. And these code can contribute differently to the overall functionality. So some code could be main contributor, some code could be auxiliary contributor. Why do we care about this contribution? Because the degree of contribution is important for understanding the relevance of an API to an access control. Main contributors are likely to be relevant to the sensitivity indicator, while auxiliary ones are less likely. And also we know that estimating this contribution extent is difficult. Like in this example, back to the same code, set secure folder is probably main contributor to this folder container because we can spot a naming similarity. And also we can spot another naming similarity to this rendered activity name. Unlike the green components, which probably are auxiliary contributors. We can, using our domain knowledge, we can make the distinction, but probably a machine would have harder time. So we observe from these motivating examples and these challenges that auditing framework APIs based on app security indicators requires reasoning about uncertainty. We cannot precisely say that a given UI element is sensitive, and we cannot state that this is an main contributor of an app. We can just speculate that it might be. How can we resolve the uncertainty? We can collect and aggregate various hints, and then we can suppress it. So we are inspired by Poirot, and we reconceptualize auditing framework APIs via app site security specification to a probabilistic inference task. Our solution, which we call Bluebird, collects various app hints to infer sensitivity of an API. And these hints could be human reasoning, a human-like understanding of an app logic, statically derived program semantics. And the inferred sensitivity is probabilistic. We can only say that an API is sensitive with the confidence C. Now, this confidence depends on how is the API invoked in the apps, what is the sensitivity of these apps, and what is the degree of contribution, and so forth. So Bluebird works as follows. We begin by statically analyzing the framework. Here we establish an initial sensitivity. We call it a prior. And we introduce a random variable to denote that an API is sensitive. Now, it could have two values. It could either be high sensitivity or low. We perform static analysis to establish these priors. Now, we audit this initial sensitivity by doing application-side analysis. So we extract evidence and clues. And evidence is a sensitivity indicator used by an app. And here is an example. UI block corresponds to a sensitive UI type. We can assign a high sensitivity to the UI with medium confidence. If the UI block contains certain sensitive words, we can assign it a computed sensitivity depending on those words with high confidence. Now, how do we compute this sensitivity? We use an NLP model. We built an NLP model that we have trained it on AOSP. Please refer to the paper for more details. Now, what is a clue? A clue allows us to transfer a sensitivity that we learned from an app to the API. For example, contribution clue that we talked about. If an API is the main contributor, we can propagate the app's component to the API with high confidence. Now, in the last step, we fuse the priors with constraint using a probabilistic inference algorithm. We aggregate the sensitivity priors from the first step, and the evidence includes from the second step to compute a posterior margin of probability. How do we detect gaps now? A gap occurs if the posterior margin of probability is more than the prior. Note that we can only say that there is an access control gap. We cannot predict the missing access control itself. All right, so finally we have, I'll talk about the evaluation results. So we applied Bluebird on AOSP to evaluate its performance. We assume that AOSP is perfectly secure, and this assumption is in line with the existing work. And we run Bluebird on 7 AOSP ROMs. Bluebird reports no gaps for 88 to 92% APIs. This means that 8 to 12% are, per our assumption, false positives. And these false positives are due to different reasons. For example, there are limitations of access control extraction that we have faced, and also apps might be overprotective, and also there might be insufficient app-side evidence. Lastly, we applied Bluebird on custom Android ROMs. So we used 7 custom ROMs from 6 vendors, spanning versions 8 to 13. And so these are the details about the ROMs. And this is the number of APIs for which we find at least one app-side invocation. The last column reports the number of gaps. So the gaps range from 15% to 44%. Of course, we want to demonstrate that these gaps could have security impacts. So we took a few cases for which we could understand the code. And we identified 11 vulnerabilities. 9 of them have been acknowledged and fixed by the vendors. The impact ranges from simple DOS attacks to modifying secure setting folders, altering power voltage, performing shutdown, and so forth. All right, so to conclude, we propose Bluebird, a security auditing tool for Android that detects access control gaps in APIs from app-side security specification. Bluebird addresses various challenges through program analysis, NLP techniques, and probabilistic inference. Yeah, I'll be happy to take questions. Thank you.